In this video, we have another example of a double integral over a non-rectangular region, but this one, we won't have the option of do we treat it as a type 1 or a type 2, and you'll see why in a second. So let's take a look. I'll just write down the problem, and then we'll take a look at its solution. So here's the problem. I'm going to set up the double integral. Instead of starting with the region, I'm going to start with the double integral, and then we'll do some sketching and then see what we have to do. So there are the two limits, or pairs of limits, and here is the function that we're going to integrate. So it's going to be the square root of x to the fourth plus 1, and then let's say, so this would have to be dx dy. All right? So this is what we're going to evaluate. Now, before we even try to do the evaluation, let's try to work backwards and actually come up with the sketch. So let's see if we can sketch this. And let's start with what would probably be the easier things to sketch. Let's start with the constants. So based on y, the limits for y, we can see that y goes from y equals 0 to y equals 8. And both of these are going to be horizontal lines, so those will be fairly easy to sketch. And then looking at x now, for the lower limit for x, we see that x is equal to the cube root of y, and then the upper limit of x is 2. So if you notice, 3 of our limits are constant, which means that these would have to be either horizontal or vertical lines, but this one is not. Now, you might know what this is, and we actually used it just recently, but I think whenever, just because of the frequency with which we graph functions of the form y equals f of x, it might be easier to put it in that form so you can recognize what it is. So if I solve this for y, I get that y is equal to x cubed. So let's sketch these 4 equations and then see what our region is, right? So let me do the sketch right over here. And so yeah, so in fact this is y equals 0. Oh, not 8, that's y equals 0. And then y equals 8 would be somewhere up here, on the horizontal line. X equals 2 is a vertical line, so over here. And notice when x is equal to 2, for the last thing that we have to sketch, if you're trying to figure out how to sketch this, you can use some, I guess I could say, yeah, use some specific points. So for instance, when y is equal to 0, x is equal to 0. So it passes through the origin there. And when y is equal to 8, x is equal to 2. So it's not a coincidence right here, so it passes through right there. And we know that this is our x cubed graph, so it's not, it looks like y equals x squared, but it's a power function, and then it goes up like this. It's not something linear, all right? So that's our graph, and then the region now. So let's see, y goes from 0 to 8, right? So it's in this region, this part of the y-axis right here. But then x goes from the cube root of y, which is this curve right here, up to the vertical line. So now let me shade this. So here's our region, and this is the region based on and if you think about it, what type is this given as? This is given as a type 2, because the y's are constant, both y limits are constant, but you have a variable for one of your x limits, right? So this is a type 2. All right, so that's the base of our solid. Now let's think about how we would integrate this. If we were to try to integrate this as given, we would have to find an antiderivative of the the square root of x to the fourth plus 1. And all I would say with that is good luck with that. This is a very difficult function to integrate. You have, in a standard Calc 2 class, none of the techniques will work, right? If this were x squared, you could try something like a trig sub, which we know, those can be challenging. But with the x to the fourth there, yeah. So I'm just going to make this point that this is not easily integrated. Can't really do it. All right, sad face. But we are persistent, we're stubborn, we're going to find a solution. So here's what we're going to do. We are going to take this, and this time I'm not going to like draw a separate graph. I'm going to keep this graph exactly the same, but instead of thinking of it as a type 2, I'm going to think of it as a type 1. In other words, shade that region vertically. So if I do this, right, then I can set this up in a different way. I could say now x goes from 0 to 2, but y goes from the horizontal line, y equals 0, up to my curved boundary there, y equals x cubed. So let me write down so here we're switching, right, or reversing the order of integration. Let me write down another double integral that's going to be equivalent to this one, where the function itself won't change, but we get to switch the order of integration. So instead of trying to do dx dy, which is very, very difficult, we're going to do dx dy dx. So the y limits now, y goes from 0 up to x cubed. So y equals 0, y equals x cubed. And then x now goes from 0 to 2. So those are our limits. And what we have in red is the type 1 way of defining our region, right? And now, just looking at the problem, remember when we're integrating with respect to y, we get to treat this whole thing as a constant. Yay, right? So this is now a constant. I'll just say WRT with respect to y. So now we're happy. Okay, so let's go ahead and evaluate this and see what comes out of it. This whole thing, again, treated as a constant. You can factor it out of the integral. And again, let me do the integral separate so you can see the process more clearly, less muddled, hopefully. So all of this, you would end up having times y when you find the antiderivative, because we're just treating all of this as a constant. So it's the square root of x to the fourth plus 1 times y. And now we're going to evaluate it at these two, 0 to x cubed. Remember, these are y limits now. So we're going to plug the upper limit in for y. So we just have that square root times the x cubed. I'm going to put the x cubed first. Actually, let's go ahead and actually keep it. Let's put the square root first. Let's do that. And then times x cubed. And then minus 0. So the nice thing is, with the lower limit of 0, the whole thing evaluates to 0. So there we go. All right. So now this is what we have to integrate with respect to x. So let me write it down. And maybe you're thinking, well, aren't we right back where we started? Not really at all. In fact, we're in a much better place because we now have that x cubed, and this is why I left it right here beside the dx, we can actually use a u sub, right? So we're going to use a u sub, and the u that we're going to choose is everything under the square root, because I have an x to the fourth, and when I find my du, I'm going to get an x cubed, right? So our u is going to be x to the fourth plus 1. So now we actually have a path forward. So let's do that, see what we end up with. So u equals x to the fourth plus 1, and then our du is going to be 4x cubed dx. I don't have a 4 in my problem. I like to rearrange this equation, my differential equation du, right? So this becomes 1/4 du equals x cubed dx. Again, also I love to change the limits of integration because conceptually it's a better way of thinking about a u sub. You're converting from one definite integral to another definite integral. So u of 0 is 0 to the fourth plus 1, that's 1. And then u of 2 is 2 to the fourth plus 1. 2 to the fourth, that's 16 plus 1, so that's 17. There you go. So here's our even more simplified integral. We factor out the 1/4 because we know that's a constant multiple. Our new lower limit is 1. New upper limit is 17. We now have u to the 1/2, and then we have our du. And now, so we've reduced this problem. I wouldn't say it's not trivial, still have some work to do, but we can definitely see the way forward. Antiderivative of u to the 1/2 is 2/3 u to the 3/2, and then we evaluate it at 1 and at 17. So at the so let's simplify the coefficient. So that gives us 1/6, I believe, and then at the upper limit we will have 17 to the 3/2, and then minus 1. And of course the 17 to the 3/2, if you like, you can write it as 17 times root 17 minus 1, but that's not necessarily at all. And then there's our value. So again, you can interpret this as the volume, net volume, if you will. I think everything is positive here, so we can say volume under, let me go back up so we can see the original problem. So under this surface, and in other words, the equation of the surface is z equals the square root of x to the fourth plus 1 over this region right here, which again, it's not a triangle or anything nice, but it's a region. It gives us a base, and we just computed the volume of that solid, right? So there are some instances where this process of switching from a type 1 to a type 2 or vice versa, it's not just that it can be done, but it would have to be done in order to evaluate. And that's usually due to how difficult it is to integrate with respect to one variable, but ends up being a lot easier when you switch it because you then get to treat that harder one in terms of treat it as a constant. All right. So hopefully that's helpful. And then next up, we are going to triple the fun. And we're going to start talking about triple integrals. So see you then.